Imagine two students given the exact same assignment. One is an experienced senior sitting in a quiet library with a fast laptop. The other is a beginner using a slow computer with constant interruptions. The assignment is identical, but the completion time won't be. Software development works the exact same way. Let's look at two 50K LOC software projects. Project A has highly experienced developers and modern tools. Project B has fresh graduates and outdated tools. If we run this through the basic COCOMO model, the estimate relies on only one input, software size. Because both projects are exactly 50K LOC, the model calculates the exact same required effort for both. But experience tells us that Project B is going to require much more time and energy. The basic formula assumes all projects of the same size require the same effort, completely ignoring the reality of the working environment. To fix this limitation, Bohm developed intermediate COCOMO. This improved model still uses the size of the software, but it introduces what are called cost drivers. These are project-related factors, like team capability and software complexity, that modify the baseline estimate. When we look at the intermediate COCOMO formula, the core math remains the same, but notice the new variable attached to the very end. This is the effort adjustment factor, or EAF. The size of your software dictates the theoretical base effort you need, but your working conditions, represented by the EAF, dictate the reality of your timeline. So how do we calculate this EAF? A software project has dozens of variables. To make estimation manageable, Bohm grouped all possible cost drivers into 4 major categories. You can remember them with the acronym PHPP: product, hardware, personnel, and project. Product attributes describe the characteristics of the software itself. Building a standard calculator app requires normal reliability. But building air traffic control software demands very high reliability and extensive testing. Hardware attributes relate to system constraints. Writing code for a standard PC is straightforward, but optimizing software for hardware with strict main memory limits requires significant extra work. Personnel attributes measure your team. Highly capable veteran analysts write better code and produce fewer bugs than beginners. Project attributes cover your management practices and environment. Using modern software engineering tools saves time, whereas working under severely tight development schedules requires extra resources to hit the deadline. This diagram shows a lot of diverse factors. In intermediate COCOMO, you evaluate every single one of these drivers and mathematically combine them into one single multiplier, the effort adjustment factor. This scale shows how it works. If your project conditions are perfectly average, your EAF is exactly 1.0. Multiplying your baseline effort by 1 leaves it unchanged. But if you have chaotic conditions, like inexperienced developers, changing requirements, and poor tools, your EAF climbs above 1.0, inflating the final amount of effort required. Think of the effort adjustment factor as a reality check. It applies a penalty for bad conditions or a bonus for highly efficient teams, ensuring your final estimate reflects the real world. Let's put this into practice with a concrete example. We need to estimate the effort for an organic project. The software size is 30 kLOC. After evaluating our cost drivers, we calculated an EAF of 1.20. For an organic project, our constants are A equals 2.4 and B equals 1.05. Before we apply the EAF, pause the video here and use the basic COCOMO formula from the last lesson to calculate the theoretical base effort first. To find our base effort, we plug the size into the formula. 30 raised to the power of 1.05 is approximately 35.6. Multiply that by 2.4, and we get a basic theoretical effort of 85.4 person-months. That 85.4 is what an average team in an average environment would take. But our project has an EAF of 1.20, meaning conditions are slightly worse than average. So we bring in our multiplier. we multiply 85.4 by 1.20. Our adjusted estimate jumps to 102.5 person-months. The specific constraints of this project added roughly 17 extra person-months of required effort to the baseline estimate. Estimating effort correctly requires this clear two-step mindset. First, you calculate the ideal mathematical baseline based on code size. Second, you apply the EAF to ground that math in reality. Let's look at this comparison matrix to see how the two models stack up. By introducing cost drivers, intermediate COCOMO moves us from a rigid, moderate accuracy baseline into a much more realistic, high accuracy estimation model. To lock this in, here is a complete cheat sheet for this lesson. Notice the intermediate formula includes the EAF at the very end. The effort adjustment factor is derived from 4 categories of cost drivers: product, hardware, personnel, and project. And remember the rule of the multiplier. An EAF over 1.0 means more effort is required, while less than 1.0 means a more efficient project. Take a screenshot of this layout for your notes. You now have a solid grasp of how to adjust for real-world project conditions. In the next lesson, we will introduce detailed COCOMO and look at how to distribute this total effort across the different phases of the software development lifecycle.